So our next group will be Mathew Chandy from UConn and Leo Cheng from here at Carnegie Mellon. And their third contributor is Lauren Okamoto, who will be in absentia from UC Berkeley. And they will be presenting their work on basketball data.
Yeah, I'm Mathew from the University of Connecticut.
I'm Leo.
And our third collaborator is Lauren Okamoto from UC Berkeley, and we were mentored by Maxim Horowitz from the Atlanta Hawks. So to begin, I'm going to provide some motivation for this project. So teams obviously want to optimize their cap space NBA teams. So it is helpful to know how much they should pay a player or how much a player is providing value. So at the time when this project was, we were doing this project, the salaries for the upcoming season, we didn't know all of them for all players. So we used salary from the 2022 to 2023 season, as that's perhaps the best proxy for how much a player will demand for the upcoming season. So teams want to see if a player is overvalued based on current output-based determinants of salary. So we're assuming that salary is generally a good way to evaluate a player's performance. But we also need to account for a team's unique needs, so we want to see how well a player will fit in with a current lineup. So our goal, our first one is to estimate if a player is over or undervalued by using a model to predict a typical salary for that player's level of output and comparing that value with the actual salary. Then we want to evaluate how players fit with each other by predicting the probabilities of events that lead to an increase or decrease in expected points, which we'll talk about later. And then third, we want to create a sort of a fun demonstration of a tool which can provide a list of recommended players to add to a four-man lineup based on the salary surplus and how much a hypothetical team is willing to pay for a player while accounting for complementary play styles.
So our overall data set is consisted of two individual data sets, and we had to do the data cleaning for each. So for the salary data set, we gather salary and performance statistics from the 22 to 23 season. And after removing redundant roles and excluding players who haven't played a significant amount of time, we are left with 317 observations. And for the play-by-play data set, we use subsets of data to answer the conditional probability questions. And in the end, we're left with 288,121 observations. So in the exploratory data analysis section, we use three main visualizations to answer three main questions. Firstly, do players in different positions get different payrolls? On the left, you can see that the distribution of salary are roughly similar among the 5 traditional positions. And the second question is that do higher player usage lead to higher salary? And the upward sloping trend are some level of indication that higher player usage tend to indicate a higher salary on overall. And the final question is, are contract values equally distributed among players in the NBA? So these two visualizations show that a majority of players receive a salary that is lower than the average level, and only a minority number of players receive contracts with extremely high values. So I'll now introduce some of the statistical methods we introduced for modeling. The first is the random forest prediction interval. So rather than using traditional point estimates, we generate the center interval predictions with 1/4 the standard average width, and we subtract the true values of players' current contract from the anticipated salary to compute for surplus values of each individual player. And the second method is clustering, which serves the purpose of investigating where there are significant gaps in player contract and surplus values among different player archetypes. So by observing and comparing the performance-based statistics, we're able to categorize NBA players into three major clusters.
So, as I said before, we want to evaluate complementary play styles or player interaction, and it is actually pretty difficult to measure this kind of offensive interaction through what most people would think passing, as NBA play-by-play data actually only records assists. So that loses a lot of opportunities for evaluating chemistry between players through passing. So one question related to interaction that can be approached is a sort of abstract interaction in terms of how a player who is inclined to commit a certain action will be affected by his teammates' propensities to commit the same action, as well as his opponent's tendencies to encourage or discourage certain actions. So an example of this kind of question is a player who is inclined to shoot a lot of three-pointers. Is he going to be a good fit for a team with mostly composed of players who also shoot many three-pointers? So the motivation for this tree here is we don't want to just see if a positive or a negative outcome will occur. We want to see the probabilities of the events that lead to a positive or negative outcome, and then the events following that would make, for example, a two-point field goal attempt is not necessarily a positive thing. It depends on who's shooting it and the probability of him making that shot. So basically, the event tree involves a split, a multinomial logistic regression at each split based on, so we have 5 players here. The 5th player could be anybody. And this is an interesting example because Ja Morant isn't currently playing. But yeah, so we regress based on the added player, the question marks, propensity to commit one, for example, for this first split, one of these 4 events. Then, based on the sum of his teammates' propensities to commit the same event, and the sum of the propensities of the events to occur against an opposing defense. And this was a method a similar method implemented in a previous paper. So the end goal is to use these probabilities and the expected points generated the points generated from the final outcome. We can predict an expected points from adding a 5th man to a 4-man lineup on offense against an average defense, and expected points allowed on defense against an average offense, and then we can find the difference to get a net expected points.
So our result shows that for the random forest prediction interval, the overall model fit is good because it produced an out-of-bag prediction error of 0.44 and an R-square of 0.64. And on the right is a list of variables ranked on their importance for predicting salaries. And there are some interesting findings that there are some of the variables that people generally might not contribute to for predicting salaries, such as the number of years a player has played in the league. And to provide assessment of players' cost effectiveness, as I mentioned earlier, we subtract the true salary value from the predicted salary to compute for each player's surplus value of their contract. And on the right, this is a preview of the player list ranked by their contract surplus and their surplus lower bound and upper bound. And there are some level of overlap between these players. So in the process of clustering and building player archetypes, we aim to investigate whether there are some level of different salary distribution between the player archetypes we construct rather than using some traditional player positions. And among the 3 main player archetypes, the primary scorers and initiators tend to receive a higher overall salary, but their surplus values are roughly similar between the other 2 player archetypes. And as you might notice that a majority of players produce a negative surplus value for their team, which means that many of the NBA players are being overpaid overall.
So, as I stated before, we wanted to create a pretty accessible tool or a demonstration of a more refined tool that could be developed by an organization. So we used a Shiny app. So our app takes 5 inputs. So an interval of salary as a hard cap and 4 players as members of a hypothetical 5-man lineup. So the algorithm was to filter out players whose salaries fall out of the desired salary interval. And then we only include players in the top 20 in terms of predicted surplus value using the random forest model. Then finally, we use an expected points model to fit on the remaining player list, and we select 4 players with the highest expected points. And here is an example of how this tool can be used. If you want to try it, you can scan the QR code. And just a quick discussion.
So the importance of this project is to evaluate if a player is currently over or undervalued and to see if a player is a good fit for individual teams. And the visualizations on the salary and surplus distributions given constructed archetypes are noteworthy as they reveal a significant divergence in salary rates, but barely any difference in the surplus values among different player archetypes. And there are some level of limitations in the project that, in terms of the clustering process, we didn't establish a clear dividing line between archetypes, and it relies on comparing the average values and integrating some basic knowledge of basketball.
Another limitation was we had a small sample size. We only used data from the last season. And for the expected points model, that's a pretty small sample size to accurately represent a player's tendencies. In addition, the Shiny app, it kind of simplifies the complexities of an NBA contract and the organizational structure to just a salary value. It's more complicated than that. So the next steps were to account for this complexity and use more data, train on data from previous seasons. We can also employ a better, more refined clustering model to construct more precise player archetypes. And lastly, for the expected points model, we can try to find predictors to improve its accuracy. And yeah, thank you to Dr. Yurko, Meg, Kwong, and Chen. He's somewhere. And thank you to Max Horowitz.